Good morning, everyone. My name is Muhammad Uzair, and I am a first-year PhD student in the University of Western Australia. Today, I will present an image set classification algorithm, which is based on compact set representation. So the algorithm is generic and can be applied to different biometric recognition and even to the task of object categorization. The outline of my presentation is as follows. First, I will introduce what is image set classification. Then I will present my proposed algorithm, and experimental results in conclusion will be given in the end. So first, let's see what is an image set. So an image set is a collection of images describing a particular class, for example, a person in biometric recognition. The figure to the left shows an image set of facial biometric of a person taken in different lighting and pose. The figure to the right shows an image set of a 3D object imaged from different views. So robust and accurate classification can be achieved by modeling the useful set variations rather than using single images. So basically, in image set classification, the gallery consists of one or more image sets for every class. The probe is also an image set and is modeled as a whole. The probe is assigned the ID of the label of the gallery set by minimizing some set-to-set distance measure. This is different from single image based classification, where the probe is a single image and is compared to individually with each gallery image for label estimation. So image set classification can offer some improvements, but at the same time, it has some challenges. The main challenge is how to efficiently model the image set compactly and without losing discrimination. And the second challenge is how to measure the distance between image set representations. So, for example, the nearest sample-based matching can fail easily if outliers are present in sets. So we will see these methods shortly. So existing image set classification algorithms can be divided into two categories: the structure-based algorithms and sample-based algorithms. The structure-based algorithms, they represent each image set with one or more linear subspaces or manifold, and subspace to subspace distance is used for comparing the image sets. These type of algorithms require a large number of images in a set with dense sampling in order to accurately estimate the underlying structure. The sample-based algorithms, they measure the distance between the closest pair of points between two images. So these algorithms are susceptible to the presence of outliers, and they require more computational power due to their inherent sample-based matching mechanism. So in our algorithm, we represent each image set by a compact and discriminative representation. So I will explain my algorithm. So let's say we have a gallery consisting of image sets belonging to C different classes. For each image set J, we have a matrix, let's say Xj, whose columns are the vectorized images of that set. We capture the first order statistics of the set using the mean, and the second order statistic using the sample covariance matrix. So the covariance matrix in this case is, so as the covariance matrix is symmetric, so not all of its elements are unique. And moreover, the covariance matrix lie on a Riemannian manifold where Euclidean distance cannot be used to measure their similarities. Therefore, we propose to apply the Cholesky decomposition on the covariance matrix in order to get a lower triangular matrix which can capture in a way the whole information presented by the covariance matrix. But before applying the Cholesky decomposition on the covariance matrix, the covariance matrix must be symmetric, positive definite. It means that all the eigenvalues of the covariance matrix should be positive. So in order to ensure that, we add some constant to the diagonal of the covariance matrix in order to make it positive definite. So one way is to add all the eigenvalues of the covariance matrix and add the sum to the diagonals of the covariance matrix. But computing all the eigenvalues may take some time, so we use a simpler measure by taking the trace of covariance matrix and adding it to the diagonal elements of the covariance matrix. The gamma here should be the size of the covariance matrix. So after regularizing the covariance matrix, we apply the Cholesky decomposition to get a lower triangular matrix. Moreover, we add the first order statistics to the lower triangular matrix, and then the mean enriched covariance lower triangular covariance matrix is, the mean enriched triangular matrix is vectorized to form the feature vectors. So in this way, for each image set, we obtain a feature vector, which is compact and is obtained by using both the first order and second order statistics of the set. So instead of using these feature vectors for classification, we perform discriminant analysis on the Gallery feature vector and learn a transformation matrix W. And the Gallery feature vectors are transformed by this matrix to lower dimensional feature vectors, in this case to C minus 1 dimensional vectors, where C is the number of classes in the gallery. The whole process is repeated for a test image set, and classification is then performed using nearest neighbor algorithm in Euclidean space. So the proposed algorithm is applied for 3 different classification tasks: for face recognition, for periacular biometric recognition, and for object categorization. For face recognition, we use the Honda UCSD database and the CMU motion of body dataset. These datasets contain videos of a face where the person moves around, his head moves around, and these are the details of the database. So we use only one image set for each person in the gallery. For periacular biometric recognition, we generate image sets from the MBGC version 2 near-infrared video database. These videos contain large illumination variations, some motion blur, and large periacular appearance variations, as can be seen by these 2 image sets. So the number of images in each set for this database is quite low, which is 4 to 17 images in one set. So we will see that the structure-based algorithms perform poorly on this dataset. For object categorization task, we use the ETH80 database. It contains 8 object categories and 10 image sets per category, as can be seen in this figure. So these are 2 image sets for the cow category. So the sample-based algorithm performed poorly on this dataset because matching individual samples may not give good results. So this table shows the average recognition rate and standard deviations of 10 experiments, where we select random gallery and probe combinations. So in the case of structure-based algorithms, they perform poorly on MBGC periacular data because the images in each set are quite low. And for the case of sample-based algorithms, they perform poorly on the ETH80 database. As can be seen that our algorithm has performed equally well or better than most of the previous state-of-the-art algorithms on most of the databases. We also compared the computation times with the previous algorithms, and the only faster algorithm than our proposed method is the DCC. However, its generalization ability is on different databases is lower than our algorithm. So in conclusion, we can say that Koleski decomposed covariance matrix can be used as a good image set representation. And the integration of first order and second order statistics improves accuracy, and our algorithm also takes less time than the previous methods. So finally, I would like to thank the MBGC organizers for the data, and ARC and the authors of image set classification algorithms for providing their code publicly available. Thank you. If you have any questions, you are welcome.
Thank you very much. So we have a little bit of time for questions. Yeah.
It's rather a general question. Have you compared your algorithm with the traditional way of doing it, i.e. you have one image at a time and then you take all the probe image and take the minimum distance?
Okay, so you mean the nearest sample based?
Instead of using a set of image in one probe as an input, use one image each time, then take the minimum distance. For example, this is the traditional way of doing it. How the results is about this?
So we are not providing the results of that experiment, but in our experiment, like for example, on the Honda data set, that algorithm only provides 94% accuracy, and the verification rate is also lower than these algorithms. So this is a way, but we are not considering the individual samples comparison in this paper.
Any other question?
How are the image sets characterized in the position subject? You say that the subject may have more subset and more image sets, and each set that has more images. How do you divide the sets? Is there a definition or?
So here in our experiments, we make these image sets from video. So a person moves his head, and we detect the faces automatically and make one set from each video. So for image set classification, the only disadvantage is that we need more images of a person.
Yeah.
Comment on the way you structure your data and using the covariance matrix. I mean, indirectly you are assuming that all the images being set follow a certain mean, and they are basically the PDF result is a case. Would that be more the case?
Yes, so that may not be the case. We are looking into that. We can cluster the images into different, like Gaussian, and then use separate means for that. But here in this work, we used single mean for the whole set. So this may be a disadvantage.
Okay, if there are no more questions, then thank you very much once again. And we move on to the next paper, which is entitled Human Identification Using Facial Comparative Descriptions. It's by the team from University of Southampton, and the paper will be presented by Daniel Lee.
Using comparative descriptions. So I'm firstly going to quickly talk over soft biometrics and our motivation behind this research. We'll then look at how facial descriptions are currently used in policing and how we can improve them using comparative descriptions. Then I'll quickly introduce the experiment and the results we've obtained. So first of all, soft biometrics is a new form of biometric which utilizes physical or behavioral characteristics which can be naturally described by humans. So these are traits like height, weight, ethnicity, and hair color. Now, a lot of previous research in soft biometrics has been in the lower left of this graph here. So we've been measuring soft biometric traits to be able to improve other biometrics. So for instance, if you're measuring gait, you might also take into account the person's height, weight, and ethnicity to slightly improve your recognition performance. Now, we're interested in the upper right of this diagram using verbal descriptions of soft biometric traits to allow identification. Now, we see one of the major benefits of soft biometrics is that it can be naturally described by humans, and it's the only biometric which that is the case. So with typical biometrics, you have a semantic gap between how we as humans describe other people and how computers describe people. So we have this gap between representation. Now, soft biometrics represents a solution to this problem, allowing us to obtain, say, an eyewitness description at a crime scene, and then automatically identify that person from the verbal description. So this is where we're sort of trying to aim for this with this research. So a bit of motivation to our research. We've already heard about the Boston bombings this morning. Now, the Boston police received hundreds of hours of video and hundreds of images from the spectators of a marathon. But along with that, they also received a lot of descriptions of suspicious-looking people. Now, their plan was to look through these video and images manually, but wouldn't it be brilliant if we could just take them descriptions, automatically search that video and image database for the people matching that description? So this is where we're sort of aiming to go with this research. So we want to take eyewitness descriptions to automatically search video footage, images, or criminal databases. So just a bit of background to this research. We've actually done quite a bit of research in this before, looking at bodily attributes, so things like height, weight, and ethnicity. Now, this paper looks at the possibilities of applying that to facial descriptions. So we've shown in the past that we're able to accurately identify people from soft biometric databases, and also we've obtained successful results for retrieval in video databases, albeit that the video was quite constrained for the body descriptions. So facial descriptions at the moment are still collected in many serious crime situations, but they do have problems associated with them. So first of all, facial descriptions are often inaccurate, and this is put down to a lack of vocabulary to properly describe facial features. Typically, after you've received a facial description, a composite is produced, so it's a graphical representation of a person who's been described. So this can be hand-drawn, or more commonly, it's computer-generated nowadays. But the problem with composites is they still require a manual identification process. So someone still needs to look through that criminal database looking for people who look the same as this composite which has been produced. So what we're looking at is taking that description and automatically doing the searching of the criminal database. So this slide is just sort of a summary of the next few slides, I suppose, and our proposed system to this problem. So the system we've generated utilizes comparator descriptions rather than absolute. Now, we've done some research in the past which has shown that comparator descriptions has a lot of benefits over absolute, and we'll come on to them in the next couple of slides. From obtaining multiple comparator descriptions, we can infer a continuous relative measurement which can be used as a biometric feature vector, and that will allow us to identify a suspect in a biometric database. So first of all, comparator descriptions. So typically when you get an eyewitness description, it will be in an absolute form. So you either get continuous estimations, so someone might say he was 6'5", or you might get absolute categorical labels, or you'll just receive something like he was tall. Now both of these have problems. First of all, continuous estimations, they have a potential of being very accurate because it is a continuous scale. But the problem is it requires a lot of skill, experience, and training to be able to accurately predict height and weight. So research has shown that on average, about 50% of estimations of height, weight, and age are incorrect. So it's not that good for obtaining descriptions. Absolute categorical labels are much easier to provide. So a label like tall doesn't require much skill. But the problem with them is that they're very subjective. So me saying someone's tall is based on my own body, what I'm used to, sort of my understanding of population averages and variation. And obviously that differs between people, so it's not ideal for a biometric. It's also not very discriminative. Because it's categorical, there's only so many labels you can use to describe someone's height. So we run into a problem of subject interference where you can have two subjects with exactly the same labels and you can't distinguish them apart. So we've proposed the use of comparative descriptions. So instead of saying someone's tall, you say they're taller than someone else. The benefits of this is, first of all, we can still utilize categorical labels, which doesn't require much skill, but it's less subjective than absolute categorical labels. So when we're comparing two people, we've specified an external benchmark by which to provide meaning to the label being used. So a label like taller has quite a defined meaning compared to tall. It's much more objective. Also, with comparisons, you can obtain multiple comparative descriptions. So obviously with an absolute description, you can only ever describe someone once, but with comparisons, you can compare them to lots of other people. And from them multiple comparisons, we can obtain a lot more information about the person you're describing. And from this, we can actually infer a continuous measurement describing that person. So we're obtaining the accuracy of continuous estimations, but we're not requiring the huge skill level required to estimate them. It also takes into account observer variables. So when you're given a description of someone, it's based very much on your own body and other psychological effects, which are reduced using comparative descriptions. So this is the data gathering website we produced. We utilize the Gate database, which along with Gate has images of the subjects' faces, front and side. We utilized 50 subjects from this database, and we asked annotators to compare a suspect, which was shown at the top, to 5 subjects sequentially. Now we asked them to compare 27 facial traits, which were loosely based on the Aberdeen face rating schedule, which is quite common in facial descriptions. We had 63 annotators provide descriptions for us, and we've collected around 300 comparative descriptions for this database. So some of the traits which are described include information about noses, ears, eyes, sort of inner facial features, stuff like that. Now, once we've obtained these descriptions, obviously a comparison only tells us the difference between two people. What we will need to do is anchor this in a population-wide scale so we can use it as a biometric. So to do this, we use the ELO rating system, which essentially takes a range of comparisons and produces a single measurement which denotes the relative strength of a suspect's attribute. Now, essentially how this works is everyone gets a default value, and that is slightly adjusted based on each comparison we receive. Now, the benefits of the ELO rating system is, first of all, not everyone needs to be compared to everyone in the database. We can obtain maybe 3 comparisons and then somehow position that person in a population-wide sort of scale. In addition, it also takes into account the person you're describing against. So if I said someone was shorter than someone who's really tall, that might not actually mean all that much. But if I said someone's shorter than someone's very short, that tells us a lot of information about the size of that person. So we calculate a relative strength for each of the 27 facial traits, and we call these relative measurements. And when we combine them, that represents our biometric feature vector, which we then use to identify that person. So this is just a diagram of, I suppose, how it would be used in applications, and we tried to sort of replicate this in our experiments. So along the left, you can see we have the eyewitness who has observed the suspect at a crime scene, and we would ask them to compare that suspect they observed to multiple subjects within a database of some sort. So this could be a criminal database or like mugshots. So from these comparisons, we would infer a set of relative measurements, which would be our biometric feature vector, which would then be used to probe the criminal database looking for this person. And from that, we'd retrieve an ordered list of people who are most similar, and then we can ask the eyewitness to identify the person. So the experiment ran very much like this. We selected a suspect randomly and obtained a varying amount of comparisons of that suspect to other subjects in the database. And the rest of the comparisons then produced our gallery database for which we're going to search. So these are just some of the retrieval results. So the dotted line here is using absolute labels. So this is sort of our baseline, what we want to compete against, I suppose. And you can see we get a 60% rank 1 accuracy, which is the same as the identification accuracy in this case. And we can see with one comparison, we're receiving 75% identification accuracy. So this is exactly the same amount of description, but we've got in a lot more information using comparisons over absolute. And as I said, one of the benefits of comparative descriptions is we can collect more than one comparison. So we can see once we've collected 3 facial comparisons, we're achieving about 97% identification accuracy on this database. And this continues as we collect more comparisons. So this just shows the identification performance with the number of comparisons which are obtained. And we can see once we get to about 5 comparisons, we're achieving about 99% identification accuracy using these facial descriptions. We also found that not only are they more informative than absolute descriptions, that the annotators preferred giving comparative descriptions over absolute. So we actually asked each of the annotators to indicate which they preferred, and you can see the vast majority preferred using comparisons. And we believe that's because the labels are much more objective and hence quite a lot easier to provide. So just to summarize, we've shown that descriptions of facial features can be used for identification, and we've achieved a 99.3% identification accuracy with 5 comparisons. Now, obviously, our experiment at the moment is in ideal settings. We're showing both of the suspect and the subjects to compare against at the same time. So in future work, we'd like to examine how these memory problems affects the accuracy of these descriptions. And also, we're very keen to be able to take a description and search mugshots in future. So we'll be looking into seeing how we can do that. So thank you very much for listening.
Thank you very much. Time for questions? Yeah.
This is very interesting work, very important. One question is, as this perhaps anti-ability, how would you go about annotating a large-scale gallery? So if you have 1 million people in a gallery, how would you get these comparative descriptors for that gallery?
Yes, so at the moment we're collecting a lot of comparisons for our small database. If you were dealing with a larger database, you'd have to start utilising that database and collect comparisons from eyewitnesses between subjects in that database. But as you say, it is quite an ordeal collecting all of that. So what we'd like to be able to do is take mugshots and from them automatically generate the relative measurements. And we've shown with bodily descriptions, bodily features, that's possible. So we can take a video of someone walking and automatically obtain these relative measurements. So one of the nice things, I suppose, with soft biometrics is that it can be obtained from lots of different sources, I suppose. So we can obtain them from descriptions, and hopefully in future we'll show we can obtain them from mugshots. But from our experience with body features, that should be possible. So that will be future research, definitely, yeah. Thank you.
Another question?
Great.
Have you considered using, say, 3D face model, which is basically movable, and you can generate different face shapes and appearances, and how would it compare with the comparison against the database?
So if we were sort of producing relative measurements from sort of 3D faces, I would imagine we'd obtain a lot more information than sort of frontal and side, I suppose. So obtaining sort of descriptions between 3D faces or potentially automatically generating relative measurements from 3D faces might be a very good idea. Give us a lot more information to go by. Yeah.
Okay. Yeah.
Have you considered giving different weights for this descriptor? I.e., when I say, I'm definitely sure that this guy is taller than that, but I'm not sure that his hair is darker than that.
Yeah.
So have you taken those into account? Eyewitness is not always sure about giving these descriptions.
Yeah, definitely. So the descriptions we actually obtained were 5-point bipolar scales. So like you'd have very short, same, tall, and very tall. So you can indicate some sort of, I suppose it's some sort of weighting to how much taller you think the person was. But yeah, definitely weighting of certainty would be very interesting, and yeah, that would be very useful in future research. Thank you.
Yes?
First of all, I would like to say it's a very, very interesting topic.
Thank you.
And it deserves as much as attention as you showed it. My question is whether you noticed if the specialties of the people doing the eyewitnessing, their education, their level of expertise, their vocabulary, does that influence the way you retrieve the scores later? And were you thinking about using some form of training for eyewitnesses in order to bridge the semantic gap that might occur between the eyewitnesses and the people conducting the training?
Yeah, so at the moment, the descriptions we've obtained is mostly from a university psychology class, so obviously quite well-educated people. So we haven't really looked at how the descriptions, the accuracy of the descriptions change with sort of different demographics, I suppose. But we were thinking for future research of putting this up onto sort of Amazon Turk and getting people from the internet to do these descriptions for us and see how that accuracy changes. And especially people aren't used to giving comparative descriptions, so it is quite a weird idea for people to grasp. So that would, yeah, definitely be interesting for future research. Thank you.
Okay, if there are no more questions, then thank you very much.
Thank you.
Once again. The next paper describes the collaborative work between Advanced Technologies Application Center in Cuba and the Institute of Automation at the Chinese Academy of Sciences. The paper is entitled Volume Structured Ordinal Features with Background Similarity Measure for Video Face Recognition, and will be presented by Heidi Mendes-Vasquez.
Thank you. Good morning, my name is Heidi Mendes and I am from the Advanced Technologies Application Center in Cuba. And this work is about the method for face recognition in video. And as Professor Kittel said, it's a collaboration with the National Laboratory of Pattern Recognition in China. This is the outline of this presentation. First, I will give an introduction and motivation of this work, and I will present the proposed method, some experimental evaluation and conclusion. Well, face recognition from video source have been a very active topic in the last year, mainly due to, yes, this picture I have been very used today, due to its application for law enforcement and commercial applications. So the benefits of using videos have been studied in previous work. First, the possibility of employing multiple images from the same person that can help to improve the performance of still image methods and of constructing more effective representations such as 3D models or super resolution images. Also, it has been seen the importance of facial dynamics for human face recognition. So the videos has the possibility of exploiting the spatiotemporal information and also the possibility of allows learning or updating subject model over the time. There are several methods that have been proposed for video face recognition. They can be divided into groups of methods. The first one only don't consider the temporal information, just consider that have multiple images. And then there are other group of methods that take into account the temporal information. Specifically, there are some reviews of video face recognition face methods, and it has been seen that the spatiotemporal method reports better results, and the importance of consider both the appearance and the temporal information in the face recognition process. The existing approach for spatiotemporal face recognition most of existing methods do not consider the local information, which is very important, have been shown that is very important in the facial recognition process. And also because in the dynamic face recognition, it should be considered that some parts of the face change, and maybe not all parts of the face images has the same weight in the recognition process. So our aim was to use local appearance methods, based methods combined with spatiotemporal representation to extract the person-specific facial dynamics. So when we analyzed this, we found that one of the few methods that used this idea was the extended set of volume LBP features, that it was the extension of the tradition of the very well-known local binary method to the case of videos. So in this case, instead of compare pixels of one images, they compare pixels from different images in the sequence, in the face sequence. So our idea was inspiring this method to extend it using the ordinal measures representation, which is a very similar idea, but like more flexible or extended representation. The ordinal measures are quite a simple concept that encode qualitative information related to the relative ordering of several quantities. In that example, you can see that it's easy to compare the persons about their height or weight, but it's difficult to say the specific difference between them. And in the case of computer vision, it's related about comparing the brightness or intensity level of images. So you can find that the first two images are more similar because they maintain the order relation of the regions, while the third images has exactly the same, the object has exactly the same bright level that the first one, however looks quite different. So in this case, what we compare is the order, if one region of the images is darker or not than the other one. This kind of representation have been applied for different biometric technologies, and in the case of faces, there are some works using this kind of representation. The structural ordinal features is one of the best performing that consider a set of ordinal comparisons and have shown to be better than LBP and other kind of ordinal representations. So compared with the basic LBP, this kind of representation, however, is very similar, but has more, as I said before, a more flexible configuration, so it can represent better the structures of the faces. So basically what we do was extend the extended volume set of LBP features so basically we add an other parameter that is the size of the regions to compare. Extended volume LBP compare pixels pixels in the same frame. For every frame of the sequence, it compares pixels in the same frame and in previous and following frames. And here what we compare is regions, using different configuration for radio, size of the region, different number of encoded frames. So this is the idea. And when we have this operator, then for representing a phase sequence, the phase is divided into several overlapping rectangular prisms of different sizes, and local histograms are computed over each of these prisms using different configurations of this combination of, as I say, all these parameters. And it is important that these histograms are normalized by dividing for the number of frames, so sequences from different sizes can be compared, which is important. And also that the histograms based on this representation will depend on the number of sampling blocks in each configuration. I mean, if it depends on the number of sampling points, it would be the number of bins that we have the histogram. So having all these histogram for each of these cubes, every histogram will be like a feature for the recognition process, and then different kinds of feature selection or classification methods can be applied. A straightforward approach was using AdaBoost method that was the same using the extended set of volume EBP features. In this case, each pair of phase sequence is compared using every histogram of these phase sequences is compared using chi-square distance, and then we have a vector with all this comparison, and they are labeled with +1 or -1 if the comparisons are or not from the same person. And then basically AdaBoost algorithm is applied to select and determine the weights for the most discriminative features. Finally, the score of each phase sequences is given by the chi-square, but using these weights learned with the AdaBoost method. However, we decide to use a more sophisticated classifier, and then we decide to apply the one-shot similarity measure, which is one of the called background similarity methods that combine the use of similarity measures with learned models, so they do not require our training data, although if you have it, can be useful. And they are they build the models on the top of distance between vectors, so emphasize the difference between them. So the one-shot similarity measure determines the similarity score between two vectors. In this case, our vectors are the histograms, by considering a training set which contain background on-label samples different from both classes. So a model is learned taking one vector with the background similarity, with the background set, and then the other vector is classified with this model, and vice versa, so they are then averaged to get the final score. That is the formulation for the one-shot similarity measure built using the free-scale linear discriminant analysis, and it was demonstrated that when doing this, it can be used with translation invariant kernel methods such as support vector machine. So in this case, the support vector machine is applied over vectors that are composed by scores given by these, one-shot similarity scores. But beside this, since it's the same configuration that we have for AdaBoost, that we have a vector composed by similarity scores, then we also can use this method to learn and classify the most discriminative features. So finally, we have done some experimental evaluation in the YouTube phase database, which is a large database composed by 3,425 videos from more than 1,000 people. And different from other video phase database, this database has different images in different resolution, scenes, pose, and expression changes. It's very, it's composed by videos from YouTube, so it has a great variability. We use the experimental protocol defined for this database, in which 5,000 of video pairs are chosen randomly, and 10 splits are made with these videos. Then one of these split are used for training and the other for testing. And we use this restrictive protocol in which we don't take into account the identity level of the person. So first we compare our proposal with the extended set of volume LBP features. So since there are not released the configuration for LBP features, we have used the same configuration for our descriptor than for extended volume LBP features. So we have obtained 60 overlapped rectangular blocks, changing the sizes with 20 pixels every time. And we have used, for first experiment, 12 parameter configuration, changing the different parameters that we have in our model. Just the only difference between extended volume LBP and our representation is on the parameter we have added, that is the size of the regions to compare. So the extended volume LBP only have one, which is 1 pixel, but we compare regions of 3, 5, and 7 pixels. You can see here the results using the extended volume LBP and our volume structural ordinal feature without Adabus and with Adabus, that of course using Adabus as it was shown in the paper of extended volume LBP feature, better discrimination can be achieved. So finally we have compared our method then using the one-shot similarity measure with both support vector machine and Adabus. And we have compared with a large number of methods that are available in the web page of this database. They provide the source code, and we compare all these methods. It is interesting here to see that this method that was the best existing before is also using a background similarity measure. That our representation, which take into account the temporal information, is better. And of course, using Adabus is also better than support vector machine because we can obtain the most discriminative features. So this is the conclusion. A new local spatiotemporal descriptor based on structural ordinal feature was proposed. We saw that this is more flexible operator than extended volume LBP, and then allows to discriminate better between different people. This operator combined with a one-shot similarity measure can achieve good results when recognizing people in video. And as future work, we are working on analyzing the influence of alignment error because, of course, all these experiments I used were done using aligned images. So we are working in the face detection process in video, so as input to this process to see how this method is sensitive to this kind of problem. And then to analyze the number of features and the large number of parameters used, using a more intelligent way to select these parameters. So that's all.
Okay, thank you very much. We have time for questions. Okay, normally if you use ordinal representation methods, you expect that images are registered in some sense. So how do you cope with that problem?
Yes, it's what I said. We will have a poster on Friday that we are working also trying to have the face detection using spatiotemporal representation. So because of course here we have an input if the phase aligned in each frame of the sequence. So that's not fair, but we are trying then to use the same representation in the phase detection and in this process in order to have a more stable representation. Thank you. And other aspect is about the computational cost that I have not mentioned. That compared with extended volume LBP, it's the only difference is in obtaining the average intensity of each region, which can be used using the integral images. And most of the complexity time is during training, because when you use the Adabus algorithm to learn the discriminative features, then it's faster the computation.
Okay, any other point or question? No, then we'll thank the speaker again. And move on to the last paper in the session, which is entitled "Can we do better in unimodal biometric systems? A novel rank-based score normalization framework for multi-sample galleries." The paper will be presented by Panagiotis Moutakis from University of Houston.
Hello everybody. So today I'm going to present our work in the area of score normalization. This is joint work with my advisor, Professor Ioannis Kakadiaris. We are motivated by the critical need to improve the score normalization performance of various techniques for unimodal biometric systems. In particular, we are going to focus on galleries that comprise of multiple samples per subject. And our hypothesis is that we can exploit the available information more efficiently to improve the performance of current score normalization techniques. So our goal is to develop a framework that works with existing score normalization techniques or those to be invented. So we are not proposing a new score normalization technique, and I want to make it clear of this point. We are refining this goal into 3 objectives, depending on the information that we use each time, and we propose a different algorithm for each case. So, as you know, each biometric system depends on a match score, and therefore, score normalization techniques, accurate score normalization techniques, have the potential to affect various domains, as you can see, face recognition and other. So our first objective, our first algorithm, the rank-based score normalization approach, exploits information from multi-sample galleries. I'm going to illustrate the main idea using an example. Each letter denotes the identity of a subject. So we have X, Y, and Z, 3 subjects. Each subscript denotes the number, the identity number of a sample. So for X, we have 3 samples, for Y, 2, and for Z, 3. When a new probe is submitted to the system, we compare it against the samples in our gallery and obtain a matching score. So these are the scores that we might obtain for this particular case. This is the first step. The second step is to compute the rank, but for each subject independently. So what we do is the following. Among the scores for X, we compute the ranks of the obtained scores. Therefore, we have 0.8, which is ranked first for X. We have 0.7, which is ranked second for X. And we do the same for each subject in our gallery independently. Then we partition this set of scores into subsets in a rank-based manner. Specifically, we compute CR using the R scores from our gallery. So the first rank comprises from 0.8, which is X2, 0.4, which is Y1, and 0.7, which is Z3. And we do the same for the rank 2 and the rank 3. The final step is to normalize each subset independently. So we partition the set of scores into subsets and normalize each subset independently. And let me show you now why this is working. This is an illustration. This is a figure where we have depicted the probability density estimates. We use a simple kernel estimation for different subsets. I just want to know that this illustration, this density estimation, is just for illustration purposes, and our method doesn't require to do any density estimation. As you may see, C1 stochastically dominates the distributions of all other of the lower ranked subsets. And this is something that in our paper we prove that this is always the case. This is based on our rank-based construction. This is why we normalize each subset independently in order to align these distributions. If we apply a simple z-score, this is the output that we get. And since the distributions are homogeneous now, we can get a better performance. So this is the main idea of our BSN. These are some results based on the BDCB database. This gallery comprises of 3D images, and we have 1 to 6 samples per subject. Specifically, we followed the following approach. We took random subsets of this gallery comprised by 1, 3, and 5 samples per subject. And we are depicting the performance as a function of the number of samples per gallery subject and as a function of the different approaches we used. As you may notice, when we employ the RBSN algorithm in conjunction with z-score or w-score, we get a higher improvement in terms of performance when we increase the number of samples. Why? Because we exploit the available information in a better way. These are the corresponding results for the same database for the task of open set identification, and these are the results for the verification task correspondingly. Now, which are the advantages of our approaches? It's parameter-free. We don't need any parameters. It can be employed in conjunction with any score normalization technique, and it's scalable because we can perform all the computations in parallel. Also, it extends W-score normalization to multi-sample galleries without having to integrate scores before applying the score normalization. However, we cannot make any inferences concerning the distributions of the subsets. And in addition, since we partition the scores into subsets, we have less information for parameter estimation. So when we normalize scores using z-score, for example, we have less scores to estimate the mean and the standard deviation correspondingly. Now, given the very encouraging results that we got, we moved one step further and we tried to exploit information from the gallery versus gallery similarity matrix. So in this case, first we have to construct the gallery versus gallery similarity matrix. We match the gallery samples against the gallery samples, and this is the matrix in gray. Then, given a new probe I, we obtain the corresponding scores, which are denoted by the vector in blue. What we do is we normalize the scores in a gallery-specific manner. In most cases, we consider the scores on a probe-wise manner. In this case, we normalize them using in a row-wise manner, and we employ the RBSN algorithm for doing this. But in order to employ RBSN, we need an identity estimation for probe I, because otherwise we cannot partition the scores in a rank-based manner. In our implementation, we use the rank 1 score to do so. Once we normalize the scores like this in a row-wise manner, we consider the probe, the raw scores for the probe again, and this time we normalize them again in a probe-specific manner, like this. Then we have normalized the scores for the same probe using 2 different sources of information. So the final step is to integrate the scores, and by using more information, we can expect a better performance. So these are the relevant results for the open set identification in the yellow line and the verification. GRBSN inherits all the advantages of RBSN, of the previous algorithm. However, we are required to estimate a probe identity to normalize scores in a gallery-specific manner. Finally, we proposed an algorithm to dynamically augment the available information and augment the gallery versus gallery similarity scores. Again, we have the gallery versus gallery similarity matrix, but this time, each time that the probe is found to be part of the gallery using some rule, in our implementation, we used a threshold. In another system, a user might manually give the probe identity. We incorporate these scores into the gallery versus gallery similarity matrices. Then, given a new probe I, when it is submitted to the system, we normalize the scores again, but this time we use the augmented gallery versus gallery similarity matrix. And we employ GRBSN as in the previous case. Since we use more information normalize scores, again we can expect an improved performance. And these are the results for the open set identification and the verification correspondingly. Now, ORBSN is generalizable. Again, we can employ parallel programming, but we have to set a threshold value to select which probes are considered to be part of the gallery versus gallery similarity matrix. And also it aggregates errors, because when we make an error, when we incorporate the scores falsely, then these errors are aggregated in the online version. Now, this is a summary of the results. Allow me to concentrate on the open set identification error. The open set identification error is inversely proportional to the rank 1 correct classification error for closed sets. Approaches such as z-score, which is a linear transformation, do not have an effect on this error because they are linear. A linear transformation does not have an effect on the rank 1 error. Our approach, on the other hand, as you can see, decreases this error significantly. We have performed statistical tests to demonstrate that for each probe, the discriminability of the match and non-match scores increases when our algorithm is deployed, and this is why we get this increase. And finally, this is a summary of the major contribution of our work. So thank you, and if you have any questions.
Okay, thank you very much.
Did you consider noise? I sort of wondered if your system could handle errors better because of the right-place formulation. So did you consider testing against noise?
In which implementation? The gallery, when we incorporate information? In which version? You mentioned noise. In which algorithm? In all of them? In this version, in this paper, we have not considered any noise.
No, I just wondered if you'd done it on the side.
Sorry.
Excuse me?
I just wondered if you'd also done those experiments.
I have done some experiments on my own, not in this case. If we add some Gaussian noise, for example, if we populate the gallery using Gaussian noise, on average, the results are the same as if we do not apply the method. So we are getting about, yes. So most of the times it depends if the assumptions for the score normalization method that we employ, if they hold. So if the subjects have Gaussian distribution and we apply this score, then we do as well or better. So this is.
Okay, there was a question there.
I don't understand why you need the estimate of the probe identity for the second and third method.
In order to apply the RBSN algorithm and partition the scores and normalize them, we need an identity, because the rank-based decomposition of the scores happens based on the rank within the subset identity. So if we do not have an identity for one of the scores, we cannot decide which is its rank to apply the RBSN. So if we do not employ RBSN and normalize the scores in a row-wise manner using simply the score, we do not need to do that. But this is another work.
Any other questions?
Two questions. One, what is the actual recognition algorithm that you use to generate similarity scores between face images?
Okay, we have used the UR3D system, which is 3D to D, and this is a work by Todd Rich and Tal, so I can give you the reference.
Another one is for your actual recognition. You have labels of subjects in the gallery. You use, knowing that the same people are in the gallery, multiple samples, you use that for your score normalization. When you perform recognition, how do you treat the multiple people in the gallery? Do you consolidate your scores together? Do you treat them independently?
Okay. First, there are two ways to address this problem. Most of the approaches so far, they normalize the scores, and then they integrate the scores based on the samples. So we will have, for subject X, 3 samples. We integrate the scores using a rule such as sum, max, one rule like this. In our case, we normalize the scores by partitioning the set, and then we integrate them. In the results that I have showed, the integration is happening all the time using the sum rule.
Some.
Yes.
There is a question at the back.
Hello. If you have multiple experts delivering scores, say between 0 and 1, some of them can be systematically pessimistic, others systematically optimistic. So when you are normalizing them, is this somehow taken into account?
Okay, first of all, this is a paper about unimodal systems. So therefore, we have only one expert. However, in the general case, we have multiple experts. The score normalization techniques, this is their main effect, that they can compensate for this effect. So if an expert gives very low scores and another expert gives very high values of scores, by normalizing the scores, we have comparable distributions, and therefore we can make uniform global decisions. Does this answer to your question?
Well, it seems to be a different problem that you are addressing.
Yeah. But right now I'm focusing on unimodal systems because this is the most limited. Okay.
Any other point? If not, then thank you very much.
Okay, thank you.
We actually managed to catch up. So thank you very much to all the speakers for their concise presentation.